Hello and welcome to this proof that the square root of 2 is irrational. This is arguably the most famous proof in the history of mankind because the ancient Greeks did not believe in concepts like infinity, and they developed the logic like the logic we're going to use today, and then someone proved that the square root of 2 is irrational. And so, for example, the decimal expression of the square root of 2 would go on for infinity. And this really caused the ancient Greeks a lot of grief. And at that point, I suppose they could have gone one of two ways. They could have either gone on the side of rejecting infinity, or they could go the way of accepting the logic that they've built up. And luckily for us, they went down the path of accepting that logic is the correct way to go. So this proof uses proof by contradiction, which is quite common in trying to prove that numbers are irrational. So before we get into the proof, I just want to sort of outline the overall architecture of it. Up here, we start off with a supposition that goes against what we're trying to prove, amazingly. So we say, suppose to the contrary, that the square root of 2 is rational. Then we have some logical statements. In fact, most of the proof from here to here is basically logical statements that just naturally flow from our supposition that we made at the top and anything else that we know to be true. So you can see here the first logical statement that follows from our supposition is that the square root of 2 must therefore be equal to p divided by q, where p and q are integers and have no common, and I've said here have no common factor, which I'll explain later. But anyway, we just have these logical statements that follow, and then down the bottom here we have where we get a contradiction. So as a result of all these logical statements, we get to the fact where we say that p and q have a common factor of 2. Now this contradicts what we said up on the second line. Either p and q do have a common factor greater than 1, or they don't have a common factor greater than 1, and they can't. Both of those statements can't be true. So the only thing that can be changed here is the original supposition, and so that must not be true. And so that means that the square root of 2 is not a rational number, and therefore it's irrational. So now let's have a look at the proof in detail. So we start with the supposition, to the contrary, that the square root of 2 is rational. So if the square root of 2 is rational, it must equal p over q, p divided by q, or the fraction p over q, where p and q are integers and they have no common factor. So by no common factor, I'm talking about the process we learned about in high school or primary school, where when you've got a fraction, you can always divide out the common factors until you get down to the fraction in its lowest term or lowest form or simplest form, whatever you call it. So however we start expressing the square root of 2 as a fraction, we can always get rid of all the common factors, and we'll end up with a p and a q that have no common factors. So now if we square both sides, we obtain 2 on the left hand side and p squared on q squared on the right hand side. Now we multiply both sides by q squared and we get 2q squared equals p squared. And I'm going to label that equation 1 because we're going to need it again in a sec. Okay, so p squared equals 2 times q squared. And we know that if a number is 2 times anything, it must be even. So p squared is even. Now we have to remember what we learned in high school, that odd times odd is odd times even is even, and even times even is even. So if we've got a number p and we multiply it by itself to get p squared, and we know p squared is even, well, the only possibility is that p itself is even. So now we can express p as 2 times m for some integer m. So if p was 200, then m would be 100. If p is 12, then m equals 6. But in all cases, if p is even, we can express it as 2 times m. So now I'm going to substitute p equals 2 times m into equation 1 up here. And what do we get? On the left hand side we get 2q squared. On the right hand side we get 2m all squared, which is equal to 4m squared. Now let's divide both sides by 2. So we get q squared equals 2 times m squared. Now we follow the same process that we used for p, but now we're going to apply it to q. Q squared equals 2 times m squared. So q squared must be even, and from that we deduce that q is even. So if we look here and here, we see that both p and q are even. But this means that p and q do have a common factor, namely the common factor of 2. And now we see the contradiction. Down the bottom, we've said that p and q have a common factor of 2, but up the top, we said that p and q have no common factor. So this is a contradiction. So the only thing that can be wrong here is our initial supposition that the square root of 2 is rational. So our conclusion is that the square root of 2 is not rational, and therefore the square root of 2 is irrational. So I hope that's helped you understand the proof that the square root of 2 is irrational. Keep an eye out. I may in the future do one on proving that e is irrational. That's a little bit harder. Or I may even do the one about pi being irrational, which is even a little bit harder still.